data called HDI rankings, which is now shared on your group. You can download that data set, and Dr. Bhavesh would use that data set. Thank you, Bhavesh. You can.
Yeah.
The gallery is all yours.
Okay, so thank you, sir. Okay, so good afternoon, all. Welcome to this, I think, second session of the day on issues in predictive modeling. What I am going to do in this session for next 3 hours is to focus on which are the practical issues that we actually face when we try to conduct the regression analysis. I presume that you have some understanding of regression because there was already one session which was conducted on introduction to regression. I am going to carry forward that contents of that session further by adding some more interesting insights regarding the problems that actually occurs when we try to estimate regression models with the different kinds of data sets. Okay, so that is the theme of this today's session, and I hope that at the end of the session at least you will carry something with you to conduct the analysis of your own in R programming. Okay, so let's begin. What I have one tablet, Wacom tablet. I will be first doing some simple theory. I'm not going to teach you all the derivations which are there in the regression, different formulas, how to derive different formulas for say for example variants of different estimators. We will stick to some simple examples, okay, and try to understand the logic behind those relationships that we are going to speak about. What do you mean by variance of estimators? Why variance of estimators is so much important? Why random sampling is important? Why OLS, the ordinary least square method, is being used in the regression analysis for the estimation of parameters. So all these things in a very simple way we are going to deal with in my today's session. Okay, so I'll start sharing my screen. To begin with, I will be using some inbuilt data sets which are there in our software already, and one data set which I have shared with you. That data set you will practice in the session itself. Okay, so you will tell me the outputs of that data sets from whatever you have learned in the session. So let's begin. I'll start sharing my screen. Can you see this screen now, white screen?
Yes, sir.
Okay, so let's begin. So the title of our session, and we'll go step by step. We are not in hurry. So for another 1 hour, I'll spend on theory, and then we'll go for the practical examples. So it is issues that we face in regression analysis. This is one kind of the predictive model that we actually use for making predictions. Okay, so the whole purpose of regression analysis is what? We actually construct the regression model with the help of dependent and independent variable. Okay, and the whole purpose of estimating that model is to predict. Say for example, you want to find out the relationship between, say, mark score by students and the number of hours he spends on studying. So here, from given date pair observations on mark score and number of hours spent on studying for, say, 100 students, you have a data on 100 students. You construct the regression model, and for given known value of number of hours study, you predict the marks that can be scored for that given hours of study that particular student has spent on. Okay, so let's begin with the regression model, how it looks like. I'll be using simple notation yi for dependent variable. We will use alpha for the intercept parameter plus beta for the slope parameter. Xi is our independent variable plus ei is the error term. Now this is called as the population regression function. This is called as the population regression function. Okay, PRF in short. Now let's call this variable y. Let's call this variable y as the consumption expenditure of families. I'm taking very practical examples that we deal with in our day-to-day life. So this is the consumption expenditure of a particular family, that is Ike family. The subscript I is for Ike family. Okay, and this X variable is actually talking about the level of income of different families. So this is the income of Ike families. Okay, so we have two variables with us. So we have the data set for Y, which is consumption expenditure of a particular family. And we have data set on X, which is the income level of that particular family. And what we are going to do over here. So this is our data set. Y is the dependent variable. We have data on consumption expenditure in terms of rupees, say 1,000, 2,000, 3,000, 8,000, then 7,000, and so on. We have data on X, that is, this is all in rupees. This is also in rupees. So we have the level of income, say 5,000, 6,000, 7,000, 9,000, or say 8,000. So we will change over here. The family doesn't spend the entire amount on consumption. So let's have some number called 4,000 over here and 9,000. Okay. And data goes on. Data goes on for n number of observations. So this is the data we have. This is the population regression function. And what do you mean by population? Suppose you want to find out on an average how consumption expenditure of families in Mumbai varies when their income varies. So what you are going to actually figure out how the consumption expenditure Y on average. The term on average is very important. Okay. So how consumption expenditure Y on average varies when the level of income of families, that is X, varies. So that is the task that you are going to conduct or perform. You are estimating the relationship between Y and X over here. So this is the population regression function. Okay, when we talk about Mumbai, there are many people who are earning some income, right? The population is huge, and they are having some consumption expenditure from that earned income. So in reality, we cannot have data for entire population. Say, for example, we cannot have data for all the families in Mumbai. Is that true? Will it be feasible for you to go to every family and collect the data on their level of income and consumption expenditure in Mumbai?
No, sir.
It is not possible. So this population regression function, we don't know. What do you mean by that? We don't know what kind of relationship is there between this consumption expenditure and the level of income for the families in Mumbai. Now there are two parameters which are very important in this regression model. This parameter, which is alpha, is called as intercept parameter. Okay, and this parameter beta is called as slope parameter. Now, how do we interpret these two? Okay, so if your income level is 0, still there will be some consumption expenditure for a particular family. So that will be equal to alpha. When X is equal to 0, level of income is 0 for a particular family, its expenditure will be equal to alpha. Consumption expenditure will be alpha. Similarly, now given alpha plus, when there is change in the level of income, say by additional 1 rupee, what would be the impact of that additional 1 rupee change in income on the consumption expenditure? And that impact of additional change in X, that is level of income of a particular family, on consumption expenditure of that family, is given by the slope parameter, which is called as beta. So what does beta tell you? Beta tells you that how consumption expenditure changes when there is a change in income level, that is X by one additional unit, that is 1 rupee. Okay. So if I actually want to draw this regression line, population regression line, I have X that is level of income on X axis and Y that is the consumption expenditure on Y axis. My intercept will start from here. So level of income 0, there is some consumption for families. So my regression line is going like this. Why it is going like this? Can someone tell me? Looking at the data.
Direct relation between consumption and income.
Sorry.
Because of direct relationship between income and consumption.
Yes. So when income is increasing, actually consumption expenditure is also increasing. Okay. So what will be the sign of this beta parameter?
Positive.
Positive.
It will be positive. Now this line which I have actually talking about is actually the population regression function, and we don't know this line. We don't know this line because we don't have data for all the families in Mumbai. Okay. So what we do, this is alpha. So when level of income X is 0, consumption expenditure is still this much, because it is possible for people, if they are not earning, they borrow and they consume, isn't it? So alpha will take some, there will be some positive value for this parameter over here. And as X changes from here to here, there will be change in Y. And that change in Y, when X changes by additional unit, is given by beta. Is that clear, students? Sorry, is that clear, participants? Not students, I'm sorry. Is that clear?
Yes.
Sir, can you repeat it once? Alpha and beta.
Okay. So what alpha talks about, if your income level of a particular family is 0, so this term will become 0, X into beta. Okay. So the consumption expenditure of that particular family then will be equal to alpha, given that this value is 0, given that expectation of EI is 0, and we take the expectation of YI also given XI. So given this relationship, EI is the error term. Now I'll come to that point a little later. The beta talks about if X changes by 1 unit, by how much quantity the Y will change. If your X, that is level of income, is 0, okay, then what will be the consumption expenditure of that particular family will be given by alpha, because this term will become 0. For the moment, just ignore this part. EI, just ignore this part. Now, what we do in regression analysis, we don't look for exact relationship, but we talk about average relationship between Y and X. So what do you mean by average relationship? It is expectation of Y, that is average of Y given X. So this is conditional expectation of the conditional mean of consumption expenditure Y given level of income, which will be equal to alpha plus beta Xi plus expectation of EI. Now these are constant. So expectation of constant is constant. Xi is known to us. So it is constant. It is non-random. So this term will be as it is when we take expectation, that is mean of these terms, and expectation of EI is equal to 0 by assumption. And we are going to see those assumptions. Right? So this is what we actually model in regression. So this is the conditional mean of dependent variable. Okay, so conditional mean gives you on an average how consumption expenditure behaves or changes when X, that is the level of income, changes. Okay, so when we take this expectation, this term will be equal to 0, and now you can say that when Xi is equal to 0, average consumption expenditure of that particular family will be equal to alpha. Okay, when Xi is there taking some value, so change in Xi by 1 unit will give you some change in Yi, and that change is given by this slope parameter beta. That is how we interpret this. So the slope of this regression line that we have drawn over here, that is change in Y upon change in X, is actually beta. It gives you change in Y when there is a change in X. Now this regression, in this way, we don't know this population regression function, Y is equal to alpha plus beta Xi plus EI. So we estimate that with help of the sample data that we have. Okay. So the moment we estimate this model, we don't have actual values for the parameters alpha and beta, but we have their estimates. So how do I rewrite this model? I rewrite this model, which is based on sample. So it is sample regression function that I am going to talk about. Is y hat is equal to alpha hat plus beta hat xi plus random error is not there. Just this much we will have for estimated value of y, or the predicted value of yi from this estimated parameter alpha hat and beta hat. Okay, and these values we estimate on the basis of the sample we have. This is our sample. This is our sample. Okay. Now we estimate these parameters in this way. But how do we estimate these parameters? The formula or the method of estimating alpha hat and beta hat is something called as ordinary least squares method, which is in short called as OLS. Okay, so we estimate these parameters applying this method of ordinary least squares method, and we estimate our population regression function. And once we get estimate for alpha hat and beta hat on the basis of sample, we predict some value for yi, and I. This cap indicates the estimate of the predicted value. Okay, from our estimated model. Now, the interesting thing is that once you have some values for these estimators alpha and beta in the population, given xi, given any level of income, say for example 5,000, you put the value for 5,000 somewhere here, and you will be in a position to predict the values for consumption expenditure for given this 5,000 level of income for a particular family. So that is how we predict this y, consumption expenditure on average, on the basis of estimated sample regression function, which is alpha hat plus beta hat xi. Now, when I estimate this model using ordinary least square method, I make very important assumptions. I make very important assumptions about the error term that appears in the population regression function. Okay, so I again write the population regression function over here, which is alpha plus beta xi plus ei. Now somebody asked, what is ei? Now consumption expenditure for ith family, we are explicitly modeling that as a function of level of income. Okay, but there are other factors which may actually influence the consumption expenditure of that particular family. And which could be those factors? Can someone tell me? Which could be the other factors that will play a role?
Education.
Family size.
Family size, exactly. Very accurate.
Age.
Family size. Okay.
Investments.
Investments.
Yeah.
Age and so on. So all these factors which are not explicitly included in the model are actually captured in this error term. So all omitted variables of the factors that actually influence the consumption expenditure of a particular family, and those factors are not actually included in the model, are captured in the error term. Okay. So all the omitted variables which actually influence consumption expenditure are captured in EI. This model is actually called as simple linear regression model. Simple linear regression model. Why simple? Because there are two variables, one dependent variable and one independent variable. We are going to see the example where we can have more than one independent variable. As you said, along with income, we can have family size as additional variable over here. If the moment I add additional variable over here, my model becomes multiple linear regression model, because I have more than two variables in the model. So it will be multiple linear regression model. I'll come to that a little later. Let us first understand this. So I make very important assumptions about this error term, and which is very important for me to make those assumptions of this EI, because EI, we don't know EI at all, right? We actually estimate EI from the estimated values from alpha hat and beta hat. So which are the assumptions that we make? We will go to those assumptions here now. So those assumptions are called as classical assumptions. Okay, so the very first assumption that we make over here is called as expectation of EI, that is error term, given Xi is equal to 0. Okay, so for a particular level of income, say Xi, the average value of EI for this given Xi is 0. So this is the first assumption we make about EI, that is the error term. So conditional expectation or the conditional mean of error term is 0. So on an average, your error is 0. That is what you have to keep in mind. The second important assumption that we make is that the variance of EI which is equal to expectation of EI square, which is equal to sigma square, is constant across X. So what do you mean by this? I am going to talk about this with the help of some graphical presentation. So it says that for every error term has a distribution, and its variance, that is the deviation of those error terms from its mean 0, is actually constant. So the variance or the spread in the data, that is dependent variable, is actually constant across X values. So that is what is meant by variance of EI equal to some constant sigma square. The moment we make this assumption, this is called as the assumption of homoscedasticity. This is called as assumption of homoscedasticity. The third assumption I make is that now, since we have data on different families, okay, in the population we have different families, and these assumptions are actually I am imposing for the error term in the population. I haven't come to the residual part of it, which is the estimated value of error term. So I'm making this assumption for the error terms in the population. The third assumption is that covariance EI and EJ, that is two error terms for two different families, which is equal to expectation EI EJ. Now I won't be going into details of all these terms. You maybe little later you can explore this. Just understand that the covariance between error term EI and the error term EJ from the population regression function is actually equal to 0. So there is the error terms are not correlated with its past values as well as future values. Now this problem of covariance not equal to 0 or equal to 0 is when we impose this assumption that covariance between error terms EI and EJ is equal to 0. This assumption is actually called as assumption of no autocorrelation. Okay, no autocorrelation assumption. Now the fourth assumption that we make about this error term is that error terms in the population are normally distributed. Actually, this assumption is not required at this time, but let's have this assumption over here so that we don't have again to go for this normality assumption. So normally distributed, all the error terms are normally distributed, so their spread will be like this. It will have bell-shaped distribution like this, all the EIs, and its mean will be equal to 0. Fifth assumption, and this is very important assumption I am making, is that the Xi, that is explanatory variable in our model, and the error term EI, they are independent of each other. They are not correlated. For every I. Okay, so error term and explanatory variable X, or the independent variable X, are actually not correlated with each other, right? So this assumption of no correlation between Xi and EI is very important to satisfy some important properties of OLS estimator that we are going to talk about. Now the sixth assumption is that not all values of X are the same. What does this mean? There is some variation in the levels of incomes of family. All the families are not having the same levels of income. There has to be some variation in the levels of income of family, and only given variation in the level of income of families, you will be in a position to figure out how the consumption expenditure changes when there is change in income. Is that correct? There has to be some variation in levels of income. So this assumption we make. Now these 6 important assumptions, let's call these assumptions as classical assumptions. Given these assumptions are satisfied, our estimator, which is alpha hat, and the formula for that is y hat minus, y bar minus beta hat x bar. This we estimate on the basis of sample. So this is estimator. And let's call this as ordinary least square estimator. Okay. Then beta hat. The formula for beta hat is summation xi minus x bar into yi minus y bar upon summation xi minus x bar square. Now these are the 2 formulas, and there is huge derivation to get these formulas. I am not going to go into details of all that. So these 2 formulas we use. We have data on x, we can calculate x bar. We have data on y, calculate y bar, calculate xi minus x bar square, get beta hat, put beta hat over here, calculate alpha hat, and so on. So we get some value, numerical value. Say for example, for alpha hat you get value which is equal to 1.25. For beta hat you get value which is equal to say 0.60. Okay. Now our estimated regression line from the sample will be now 1.25 plus 0.60 xi. Okay. So for every additional increase in level of income by say 1 rupee, consumption expenditure actually increases by 0.6 paise from our estimated model. So this model we get the estimate for alpha hat and beta hat using OLS estimator by assuming that all these assumptions are satisfied. If all these assumptions are satisfied, we say that the OLS estimator of alpha hat and beta hat given by these formulas, 2 formulas, is actually best linear unbiased estimator, which is also called as BLUE. What do you mean by this blue estimator? If all these classical assumptions are satisfied, the OLS estimator is linear. It is linear independent variable. Why? Okay. It is unbiased. Unbiasedness means that expectation of beta hat is actually B. And I'll come to this point. Efficient. E stands for efficient. Efficient property implies that the OLS estimator of alpha hat and beta hat is actually having minimum variance. Okay. It has minimum variance. So this property, and there is one more property along with this, is called as the consistency property of OLS estimator. So all these are the properties of OLS estimator. Just brief demonstration for 1 minute or 2 minutes. How do we get alpha hat and beta hat? This is X, this is Y, this is your sample. Since there is positive relationship between X and Y, it is actually trending up. So this scatter is actually going up, okay, with X. You fit this line. Now fitting this line is actually nothing but estimating alpha and beta in the population regression function and calculating Y hat is equal to alpha hat plus beta hat xi. So this is our sample regression function. On the basis of sample, we have done that. Okay. Now here, if you see that for given level of income, say 1,000, predicted consumption expenditure is Y hat from our model. It is on this line, but actual consumption expenditure may differ. It may be somewhere here. For given level of income, say 2,000 rupees, your predicted value is somewhere here, but actual value is somewhere here for that level of income. So your actual Y and your predicted y may differ. It may differ. And the difference between y actual and predicted is actually called as residual, and it is indicated by E hat I. And this is an estimate of error term in the population regression function. So difference between actual y and that one predicted by your model give you the error that you have actually encounter, and that error is E hat I. Okay, so this is how we estimate this. And the ordinary least square method actually tells you that the principle of ordinary least square method tells you that you minimize E hat I square while choosing alpha and beta, but while choosing values for alpha and beta. So what do you mean by minimizing E hat I square? Can someone tell me summation of E hat I square while fitting this line? I want error to be minimized, or the distance of actual values from the fitted values to be minimized. So what does that mean?
The true value is the predicted value is close to the true value.
Exactly. So we applying OLS principle, that is ordinary least squares principle, we are actually choosing the values for alpha hat and beta hat in such a way that these actual data points are actually very close to our fitted line, that is estimated value. Why? So that is the principle we apply, which is called as the ordinary least square principle. And the least square implies that the deviation of actual values from the predicted values should be as minimum as possible. So we minimize this total distance of yi's from predicted yi's by taking some derivative, and we calculate alpha hat and beta hat. I'm not going to explain that over here. So this is how we arrive at alpha hat and beta hat from the sample regression line that we have fitted for this. And this, the line should fit the data well. That is what we desire, isn't it? Your actual and predicted values should be close to each other. Then there is a less error that you have actually encountered, or got in the estimation of this sample regression, population regression function. Now, if these assumptions are not satisfied, we are saying that if assumptions are satisfied, the OLS estimator is unbiased, it is efficient, it is linear in Y, this the important three properties are satisfied. Now, what do you mean by unbiasedness of beta hat? Now, this is one sample we have picked up, and we have estimated beta hat. I can go to some different areas. If, for example, my first sample is based on a sample from Santa Cruz of say 100 families. I estimated my regression model and calculated beta hat and alpha hat from those 100 families from Santa Cruz. But next time I may go to some other areas. Say, for example, I go to Dharavi and I picked up a sample for 100 families from there. I'll get different values for beta hat and alpha hat. If I go to say Thane, pick up sample for 100 families again, I'll get different values for alpha hat and beta hat. So along with my sample, across samples, the values for alpha hat and beta hat changes. So the point I'm trying to make over here is that beta hat changes from sample to sample, and since it changes from sample to sample, it is a random variable. It is called as random variable. The moment we say that beta hat is a random variable, it will have probability distribution. Okay, so we say that beta hat probability distribution something like this. So here we have beta hat from different samples, and we are saying that if all these classical assumptions are satisfied, expectation of beta hat is equal to b beta. Now, what is beta? Can someone tell me what is beta?
True value of population parameter.
True value of population parameter. We don't know that, but this estimator has a property. The beta hat estimator has a property which says that on an average, if you average the values of beta hat from different samples, that average will be equal to your true population parameter, even though we don't know beta. Okay. Excuse me, can you give me 2 minutes? I'll be back in 2. Just give me 2 minutes. I'll be Okay, sorry for this uh, disturbance. I'll get back to our derivation here. So here the expectation of beta hat is B, that is equal to true parameter, and that is what is meant by unbiasedness property of beta hat. So beta hat is actually unbiased estimator of true population parameter beta. What do you mean by efficiency? It has minimum variance. The beta hat has minimum variance. What do you mean by that? Beta hat is having minimum variance because the beta hat is actually spread around this true population parameter beta. So the beta hat is actually scattered around this true beta, and we are saying that spread of beta hat around this true beta is minimum by this property of efficiency. So the OLS estimator beta hat is actually having the minimum variance from this property of efficiency. And this is very important property that you must keep in mind, that the spread of estimated or the predicted value for beta, which is beta hat, around true population parameter beta is minimum when we have OLS estimator. Okay. And along with this consistency property also is there, and it is called as large sample property. It says that as sample size increases, as n, which is equal to sample size, increases, okay, your beta hat gets closer to true population parameter beta, which implies that limit of beta hat as n tends to infinity, limit of variance of beta hat as n tends to infinity is equal to 0. So variance is actually getting equal to 0 or close to 0 as sample size n increases. So that is what is meant by consistency property of OLS estimator. As n, that is sample size, increases, your beta hat moves or gets closer and closer to the true population parameter beta. Okay. Now these are the properties. The moment we relax some assumptions, these properties, some of these properties are still satisfied, but some of these properties are not satisfied. And that is what we are going to see now. And that is the whole purpose of this session on issues in regression. So the first property that we are going to relax is the property of constant variance. That is this property. Now, what do we mean by this property? If you go to population regression function over here, now this is in the population, these are actually estimated values, and population regression function, this line we don't know. But for example, say that there are some values are like this, scattered around these conditional mean values. These are y's, actual y's, and these are the expectation of y given x. So these are the mean values, and this is the actual value. So deviation of actual from mean will give you EI, which is error. Or in short, you can say that this is for the sample, this is predicted value, and this is actual value. So for the population, this is called as error term EI. There is no hat over here because it is not based on estimation.
So could you please redraw the diagram? It is not very clear.
This one?
Yeah.
Okay. So let me get some good space for that. So this is your X, this is Y, this is population regression line, this is your alpha over here. Okay, let's call this as Y, let's call this as expectation of Y given X, which is equal to alpha plus beta Xi, and this is population regression function. Okay, now we have different levels of incomes of families over here, going from 1,000, 2,000, 3,000, and so on up to say 10,000 and above that. Corresponding to these levels of income in the population I'm talking about, we have number of families having different consumption expenditures. Because some families may earning 1,000 may spend 500, but there are some other families who just spend 300 in the population, isn't it? So their expenditure varies even though the level of income is the same. and we have this, and this is the population I'm talking about. We don't know this. This is just the hypothetical or imaginary kind of thing that I am demonstrating over here. This is your conditional mean, expectation of y given x. So it is the mean of all these actual consumption expenditures given x at this level, and this conditional mean is given by these circled values. Okay, and the deviation of your actual consumption expenditure of that particular family from this level, from this mean, is nothing but EI, error term. And we are making some assumptions about this error term in the population. Now we are saying that each error term, uska spread along its around its mean is constant. So it says that variance of EI, which is equal to expectation of EI square, is equal to constant sigma square. Now, given this assumption of homoscedasticity, we get values for alpha hat and beta hat. But now we are relaxing this assumption. What we are saying over here, error terms EIs are actually having different variances across X values, that is the levels of income. So expectation of EI square, which is nothing but the variance of EI, is now sigma square with the subscript I. The moment we have this subscript I, this or homoscedasticity assumption is violated, and if this variance of EI is changing with X, this is called as heteroscedasticity problem. This is called as heteroscedasticity problem. Now, what do you mean by heteroscedasticity problem? Just go to the sample. Just go to the sample example. This is X variable, this is Y variable, this is your sample regression line. Y hat is equal to alpha plus beta xi, alpha hat beta hat. You have something like this. Now you tell me, these are your data points. Assume that these are your data points. This is X, that is level of income, and this is Y, which is consumption expenditure. Okay. Now, as X varies, what is happening to the spread of Y or the variance of Y?
Increasing.
It is increasing. So
It
what
is
I mean
also, yeah,
yes, please.
It is
It is
also
also-
deviating from the standard line of
yeah, it is dispersing,
So what does that mean? It
the
is
standard
dispersing
error
means,
of estimate is increasing.
going away from that mean line now.
yeah.
line.
So in the sample, if you see, as X increases, Y is increasing on an average. That is true. Therefore, we have this positive slope line. But the spread of Y is also increasing with X. So if you see that at higher levels of income, there are some families having some consumption expenditure, but the consumption expenditure of families with high level of income is greater than the consumption. The variation in the consumption expenditure of families with higher level of income is actually very high compared to the variation in the consumption expenditure of families with a low level of income, somewhere here. So the data points which are giving you the consumption expenditure at this level of income, the variation in these data points of Y is less than the variation in these data points of Y given X. So what does this mean? The variance of Y at this level of income is lower compared to the variance of Y at this level of income. Y is consumption expenditure. So the rich families having lots of variation in their consumption expenditure for given corresponding level of income. Poor families don't have much scope, and therefore they have low variance in their level of consumption expenditure. The low variation in the levels of low variation in the consumption expenditure for this lower income, the poor families. So when this type of data you have in your sample, you are going to encounter the problem of heteroscedasticity. Problem of heteroscedasticity. Okay. Now you will wonder that it is Y that is its variance is actually different, but remember that the variance of Y is actually the variance of EI. I'm not going to go into details of this. Just this equality hold, and you can, I will ask you to refer few books and you can read and understand this. Just assume that the variance of y is actually the variance of ei. So it implies that the variance of ei is actually changing with x. So the variance of ei, error term, is actually sigma square I. I subscript implies that for every ith family, the variance of the error term is different. So it changes with x. Now, if this kind of problem is there in the regression estimation or the regression analysis, your OLS estimator, if you use this data set and apply OLS, okay, you get value for alpha hat and beta hat. These estimators for alpha hat and beta hat will be still unbiased in the presence of heteroscedasticity. So expectation of beta hat will be equal to B. They will be still consistent. But the important point is that they will be no longer efficient. The estimator beta hat will be no longer efficient. The OLS estimator. Yes, please go ahead.
Sir, and will ask you price consumption depends on the market price or market value.
Sorry.
How can we estimate the research at poor people's expenditure depends on their incomes. So how can we analyze the price consumption?
It is not price consumption, it's consumption expenditure of families
Families.
at market prices.
At market price.
So they are whatever they are spending.
So market price also it depends on the location wise or
Yeah, it depends. It depends. Market price. Yeah. So that is why I'm saying, no, you get different values for alpha hat and beta hat because of different values for consumption expenditure and level of income.
yes.
So that's true. So it is no longer efficient, and this important property of efficiency is violated when it is not efficient. The beta hat estimator is not efficient. Okay. Its precision will be less. The precision in the estimation of beta hat will be less. You are less precise in your estimation of beta hat from given sample when it is not efficient. And what do we mean by not efficient? It doesn't have minimum variance. It doesn't have minimum variance. Okay, it doesn't have minimum variance when there is a heteroscedasticity in the data. Now the minimum variance when there is homoscedasticity. When there is homoscedasticity, that is all error terms are having the same variance. The variance formula for beta hat is actually sigma square I upon, sorry, sigma square not I, sigma square upon summation xi minus x bar square. This formula we derive for variance of beta hat when there is homoscedasticity, but under heteroscedasticity, this formula will not work. So variance of beta hat will not be equal to sigma square upon summation xi minus x bar square. This was the minimum variance given by this formula under homoscedasticity. But the moment there is heteroscedasticity in the data, this formula under heteroscedasticity will not be equal to this minimum variance formula. Therefore, the OLS estimator will not have minimum variance. Will not have minimum variance. And the precision will be less in the estimation. Okay. So this problem actually, that we have to keep in mind. So now once the heteroscedasticity is there in the data and we say that the OLS estimator is not efficient when we have heteroscedasticity, how can we proceed actually? the first thing that you actually have to see is that you have to test for the heteroscedasticity to confirm that there is a present, you have the heteroscedasticity in the regression model. So testing for heteroscedasticity is the first task that you must do. Okay. Once you test for that, and there is a very important test that you can actually refer to, is called as Brush-Pagan-Gottfried test. The test is called as Brush-Pagan-Gottfried test. I think I will have to, yeah, it is BREUSCH Pagan-Gottfried test. Okay, this test we apply to actually test for the presence of heteroscedasticity in the regression model. Test for the presence of heteroscedasticity in the regression model. Once you apply the test and it says that there is heteroscedasticity in the data, if test says that test results actually confirm that there is heteroscedasticity in the regression model, you go for some other estimation method, not the OLS. The one thing you can do is you can go for heteroscedasticity consistent robust errors. Heteroscedasticity consistent. These are little technical terms. Don't worry about it. When we go to the actual example, you will understand these very well. Heteroscedasticity consistent robust errors. Or you can go for other estimation method, which is called as GLS, that is generalized least square method. Least squares method. Okay, and there is one specific type of this generalized least squares method is called as weighted least square method. Which is WLS. Now, when the heteroscedasticity is actually present in the data regression, the model suffers from the heteroscedasticity, we go for, instead of OLS, we go for generalized least square method, and one specific type of that generalized least square is the weighted least squares method. So we weight error terms according to its variance. So the error term with high variance will have lower weight in the estimation. The error term with low variance will have higher weight in the estimation, because we want to minimize the variance of estimator. So that is how we use weighted least square method. I won't be going into detail of this again, because that will take lots of time. And I will keep it as simple as possible. Here, you just correct for the errors that have we have the standard errors for coefficient. You just correct for those coefficients. We will have a look at this method. We'll have a look at these tests also. We are not going to do this. Okay. So heteroscedasticity consistent robust errors, or the heteroscedasticity consistent robust estimates for standard errors for OLS estimators, we can actually compute that by accounting for heteroscedasticity, and then we can actually infer the test statistics for the statistical significance of parameters. The important thing is that if heteroscedasticity is present in the data, okay, and you want to test for, now you have estimated your model. It is alpha hat plus beta hat xi plus ei, xi, applying OLS, ignoring that there is heteroscedasticity in the data. Okay, you estimated the model using this same method OLS. You go for the statistical test of the statistical significance of parameter, the estimates alpha hat and beta. So you construct the test as beta hat. Say for example, your H0 is beta hat is equal to 0, and H1 is beta hat is not equal to 0. So saying that under null hypothesis, income is not having any impact on consumption expenditure, and in there you are saying that under alternative, that income is having some impact on consumption expenditure. So the key statistic that you are constructing is like this standard error of beta hat. Okay. Now this standard error of beta hat is actually based on this formula for the variance of beta hat. This formula for variance of beta hat which is equal to sigma hat square upon summation xi minus x bar square. Now this formula we know that will not hold when there is heteroscedasticity. So if you still apply this formula in the statistical test, your test results will go wrong. And this is important implication of heteroscedasticity in the regression model. Your test results of statistical significance of this parameter estimators beta hat and alpha hat will go wrong if you continue with the earlier formula for variance of beta hat that prevails when there is homoscedasticity in the regression model of the sample that you have. Is there any question so far? This is important implication of this. I'm not going into detail of all this because it will take lots of time. You can explore this, but you have to keep the things in mind sequentially. What do you mean by heteroscedasticity? That error terms variance changes with x. What are the implications of heteroscedasticity? Important implication is that the OLS estimator is not having minimum variance, so it has less precision now under heteroscedasticity. How to solve the problem? First, test for the heteroscedasticity by using this test of Bloch-Pagan and Goldfrey, and then go for either heteroscedasticity consistent robust errors or go for generalized least square methods, under which you have method called as weighted least squares. So these things you keep in mind. And another important repercussions of heteroscedasticity that you will encounter is that your test hypothesis test for this statistical significance of parameters alpha hat and beta hat will go wrong if you continue with the original formula of variance of beta hat. Is this clear? Is there any question?
So could you let's do something practical so that whatever you said.
Yes. I'm going for the examples now only. So if
Yeah.
there is anything that you want to ask over here, you can ask.
Otherwise, yeah.
Yes.
You mentioned in between that you tell us about some books.
Yes,
Yeah.
actually, the one book that I have referred to is actually the book of econometrics, and the example also I have talked about is from that book only. So I thought it will be very easy for you to refer to that book to understand the example which I have given in the class.
Okay.
So the book is this. I'll give you the details of this book maybe a little later. That the author is Damodar Gujarati.
Okay, fine.
Yeah, Damodar Gujarati, basic econometrics. You will understand all these details very well if you go to that book. Because I have taken the example from there, so that you whenever you have time, you can go back and have some understanding of that as well from the book.
Thank you.
So yeah, so now once this is done, let's move towards the practical example. Okay, so now move towards the R software. So I'm using R Studio. I think everybody is having R Studio or base R installed with you, isn't it? Is that true?
Yes, sir.
Okay. So now we will use two data sets. First, we will use one data set from package called as Wooldridge. Now, Wooldridge is again very famous author who has written a very good book on econometrics, introductory econometrics, Jeffrey Wooldridge, and that book is having lots of practical examples from our day-to-day life, and we will pick one example from that book, and the examples from that books are actually included in this package called as Wooldridge. Okay, so install package. I will just maximize this font over here like this. Yeah, is it visible to you now? Can you see the screen?
Yes, sir.
Okay. So now first you will have to type the command install packages. Let me do that for you. Not for you, for me. So install dot packages, and the package name is Wooldridge. Package name is Ulrich. If you press Control Enter, the RStudio users press Control Enter. This package is already being installed in my this thing, so I don't have to again go for this. But yeah, it is being installed. Once this package is installed, load that package by using command called as library. Library Ulrich. So package is downloaded in my case. Then to load this package in our search path, in our memory, I just again type the command library Ulrich and press Control Enter. Okay, are you with me?
Yes, yes.
Okay, so now there are lots of data set in this package. So just type help library, help package Ulrich. Okay, so you see that the screen is opened on the right hand side to the bottom. Has it opened for RStudio users? So these are the different data sets which are there in Ulrich package. Okay, and we are going to use the data called as savings. Data called as savings. So let's go to that data set which is their saving. Have you figured it out? In S series, there is a data set called as saving. So just click on that data set. You will get the description of data. What kind of data is that? So it is the data on saving, data frame with 100 observations on 7 variables. Saving, annual savings, annual income, family size, education, years, and so on. We are going to use first two variables, that is savings, annual savings in dollars, and the income, annual income in dollars. Okay, and these are the data for different families. So it is a cross-sectional data that we are talking about. And the cross-sectional data actually encounters, when we have cross-sectional data, we actually encounter the problem of heteroscedasticity. So see this data, what type of data we have. Just type data Ulrich. I'm sorry. Sorry, not data Ulrich, data savings. Now to see this data, you just type saving.
Hello, sir. Hello.
Yes.
Sir, from
Yes.
where did you get this data savings?
From the package Ulrich. Have you installed package Ulrich?
Yes. Just now I have installed it.
Type this command called as, or just go for data saving. Type this data double inverted comma savings inside the bracket. If you all are ready, tell me. I'll wait for some time, 1 or 2 minutes, to give you some time to get the data loaded. So this is the data we have. This is the data we have. We are going to use this first two variables, savings and income, for the different families. And to do that, I use some little complex R command, and you don't have to go into details of that. Okay, You don't have to scratch your head for that. You have to scratch your head for interpreting the output of this command.
So I have typed data saving, but it is not showing any kind of data.
It must show. See, have you installed package correctly?
Yes, sir.
Then have you used that command data inside the bracket double inverted comma Woolridge?
Yes.
Then type data, not Woolridge, I'm sorry, the savings data, like just type the name saving inside the double inverted comma.
That I've done, sir, but nothing
Okay,
is
now
turned up.
again type name of the data set saving below that.
Okay, I will try that.
Yeah, after we type saving, we are getting the data.
Yeah, you have to type saving, then the data will appear. Now if suppose you want to see which are the variables which are there in the data set, just type call names. Call names, data names, saving. So these are the different variables, and we are using save and inc. These are the two variables, savings and income. We are going to extract from this. Okay, so let me go for doing that. So what I do, I install two more packages, and you will also have to do that with me. So library dplyr you will install. So install dot packages again. dplyr is the first package you will install, and then next install dot packages. The next will be called as ggplot2. ggplot2 is very powerful package for visualization of data. Okay, there is an error. I forgot to put double inverted commas. Let's install these two packages. This package is already been there in my case. Now to load this package, I just type library dplyr. Now to install second package, install dot packages ggplot2. Control enter. Which one? No, to load the to load that package, you have to run library ggplot2. You have already. Oh no, you just type it once. I actually taken it down. You just type it once. Don't do it twice. Okay, so to load this package again, library ggplot2, I will do that. Now I'll go to from this given savings data, I just want to pick up all the positive values for savings and the values for income which are less than 20,000, just for simplifying the things. And we are picking the values for savings such that saving is less than income. So we are filtering our original data by applying this command savings. So this is what we have. The command is saving. You can write this command together like this instead of one below the other.
Could you also please post it in the chat box so that it becomes easier for us to?
Copy.
Yeah.
I can do that. In fact, I should have shared this file with you, but the problem is that अगर मैं share करता तो आप कुछ सीखते ही नहीं है इस session में पूरा. So that is why I purposely tried to not share that with you. But now I should share because something you have understood how the R works or something like that. So here I am testing that command. Okay. Okay, so what I am doing over here, I am using this command called as saving percentage greater than percentage filter. Save is for saving. So from the saving data set, this is something called as a forward pipe command. I am not going into details of that. Filter, the saving is greater than 0. So positive values for saving we are extracting. We are extracting values for income which are less than 20,000. And also we are saying that your saving value should be less than income value. That should be the case, isn't it? You can't save more than what you want. So when I run this, I get savings data ready for me. I get savings data ready for me. Okay. So now what I do, I attach this data to search path. So attach data saving over here. I run the regression model now. So I'm regressing. I'm actually finding out how savings on an average change when the level of incomes of the people change. Okay, how savings changes when the levels of incomes of people change. This is again the practical example, very simple example to understand. There is a positive relationship between the two. Ideally, it should be positive by theory. We are going to see whether it is positive or not by actually looking at the data. So my regression model, let's call that model as N1. LM is for regression model, linear regression model. My dependent variable is save for saving. My independent variable is IMC for income, and the data that I am using is saving. Okay. If I run this, now have a look at those results and tell me what do you see in those results.
Bhavesh, can you paste this command if you don't mind?
Sure. I'm sorry. I'll just go to that. Actually, yeah. So this is the regression model that we have estimated. We are regressing saving of families on the level of income of families from the data set called as saving.
Yeah, if you can just copy paste that M1 and summary M1.
Sure. I will do that. Is sir is there? I will actually email this thing, whole file to sir so that you can do that easily with me. I will just.
So you can put the file in the chat box.
Is that possible?
I think so.
I'll just do that. Oh, it is not happening.
Bhavesh sir, I just give you my email ID. You can send it to me. I'll put it on our WhatsApp group so that everyone has it.
Where is just wait.
I just put the email ID in the chat box.
Okay. I'll stop sharing for a moment.
Yeah.
I have sent the file just now.
Okay, sir. I just
Have you received the file?
not yet, sir.
It has been sent on your this email ID.
Yeah, I'm just checking. I just refreshed it, but it's not. I haven't received it yet. Yeah, the email ID is correct.
So by
So you can post it in the chat box. We are okay with it.
okay, so I'll do that. But if
Please
file is
proceed it.
okay, but I have sent the file. If that comes, that will be good. But
Yeah,
I'll
yeah.
still post in the chat box.
Yeah, that's
So-
better if you post it in the chat box. So that
have you-
simultaneously we also do it.
So you got the results like for summary M1.
Yes.
Very good. So what kind of
Yes.
relationship is there between income and savings?
Positive.
Positive.
There
Yeah,
is a
positive.
positive relationship. So for
Yeah.
every additional dollar of income, saving increases by 0.14 cent.
Yes.
Bhavesh,
Yes.
Yeah.
if you look at the GG plot, and I'm not sure whether what I'm saying is right,
Yes.
can we assume, okay, where we have not, I think we have not done a test of heteroscedasticity. Looking at the plot, can we assume that there is heteroscedasticity? There would be a likelihood of.
Yes, sir. Actually, that interesting thing I want to show now because what we do, we have not considered for heteroscedasticity and we have estimated our model. Okay, so without considering for heteroscedasticity, we have got these results.
Right.
And we know that if you ignore heteroscedasticity, these standard errors, which is variance of beta hat, will be different from the OLS standard errors.
Right. Right.
Correct? So अभी क्या करेंगे? We'll see if there is heteroscedasticity or not with the test as well as plot. So execute this command, ggplot, control enter. You have this command already with you, right?
Yes, already plotted.
Okay, okay. So now from the plot itself, it is very clear what is happening to the pattern of that data. If you go along the x-axis, income increases. What is happening with the annual savings? On an average, annual savings is increasing, but the spread is also increasing.
Yeah.
मतलब उसका meaning क्या है कि rich families having lots of variation in their savings compared to poor families, because they have lots of options. They can explore lots of options of savings, so they have lots of variation in their savings compared to poor families. So there is a problem of heteroscedasticity in our data set. Okay. Now, how do we test? Now, this visual understanding is fine, but still we want to test it with the help of some econometric test, and that is called as Bruce-Pagan-Godfrey test that we are going to perform now. So, go to the test. You will need. I'll come back to that. Experience. Testing for heteroscedasticity. So you will have to have library LM test. Please install that. And there is a command called as Bruce-Pagan test, that is BP test, to do that. So library LM test, you will first install, and then go for Bruce-Pagan-Godfrey test. You have, if you have already installed, you don't need, you just use library. But if you have not installed, then you will have to type that install.packages. LM test. Sorry. Kia install, then use the command BP test, and our model is not M1. So yeah, our model is M1. So I write inside the bracket M1. So this will give me, sorry, I have to run the library LM test. So library LM test is done. Then BP test. Now this is the test result. Now the null hypothesis under this test is that there is no heteroscedasticity. And the alternative hypothesis is that the model suffers from heteroscedasticity. So do we reject or fail to reject the null hypothesis in this case from the results? The p-value is less than 5%.
So we reject?
We reject the null hypothesis by saying that the model suffers from heteroscedasticity. Model suffers from heteroscedasticity because p-value, going ahead with the 5% level of significance, the probability of committing type 1 error, that is wrongly rejecting the null hypothesis, is very low, 0.04, less than 5%. So you reject the null hypothesis in favor of alternative. So even our test result also confirms that there is heteroscedasticity in the regression model. Okay. Now there are two ways, as I said. You go for weighted least square estimation, where we give different weights for the error terms, and those weights are inversely proportional to their variance. So the error term which larger variance will get the higher weight, lower weight, and the error terms with the lower variance will get the higher weight in our estimation. You go for that. But before that, there is one method you can use, is called as getting robust t-test of the heteroscedasticity consistent robust errors. Heteroscedasticity consistent robust errors. And to actually get the heteroscedasticity consistent robust error, you will need the package called as sandwich. You will need the package called as sandwich. Okay. So just install .packages.
One request to you, will it be possible to also write why we are adding those commands?
Madam, it will take lots of time. I won't be able to teach what I actually should be teaching in the session. But you can mention on your own, maybe, because there are lots of commands that I have to actually execute. So that won't be possible for me. So install .packages, sandwich. No, because this package is already installed in my PC. So I load this package called as library sandwich. Okay. And this package, there is a command called as coefficient test variance covariance matrix. And this will give you the robust standard errors which are adjusted, which are heteroscedasticity consistent. Just for the moment, ignore this type. Sorry. We are doing this for model 1. So sorry, instead of M2, you have to put M1. Instead of M2, you have to put M1. I run this. If I execute this, please complete the bracket. So there will be double bracket in the end. Sorry, symbol. Now, compare the standard errors from this estimation with the standard errors of our earlier OLS estimation. Both are OLS estimation, but we are using standard errors over here, which are heteroscedasticity consistent now. So compare these errors with the earlier one. Compare this with this. किसका स्टैंडर्ड एरर ज्यादा है? कैन समवन कंपेयर एंड टेल? ये हेटेरोस्केडेसिटी कंसिस्टेंट है, मतलब हेटेरोस्केडेसिटी अकाउंटेड एंड देन वी एस्टिमेट दैट दोज वैल्यूज.
First test.
The The first one, that is heteroscedasticity consistent, has given us the standard error, which is higher or lower?
Higher.
It is 4.43, and below it is 4.62. It is 0.046, and upar wala 0.05. So I think this is higher, right? Because we have accounted for heteroscedasticity, it is heteroscedastically consistent. And this was without accounting for heteroscedasticity, this one. Understood the difference between the two? Yes or no?
Yes, yes.
We can take a break. We are done with the heteroscedasticity part. The weighted least square I'm not going to do. It is little complex, and we don't have time to go into weighted least square also. I think it is better to cover some other issues along with this, because the main issue you have understood. What do you mean by heteroscedasticity? How to handle it and all those things? This is
Yes,
one way
yes.
of, this is one way of getting solution from solving heteroscedasticity, and there is another way, which is weighted least square estimation. That you can do that in R, but it is little complex. I haven't actually done that, and maybe you can explore that on your own if possible. I'm not doing that over here.
Sir,
So let's, yes.
Sir, just in 1 minute, in robust test with the heteroscedasticity, we tried to do the regression. What we did in this robust test?
What we have actually done in that robust test, we are actually estimating those different error terms from the different error terms, that is sigma square I, from our sample, and we are putting that into the sample. See, the formula for variance when there is heteroscedasticity is sigma square I into summation xi minus x bar square upon summation xi minus x bar whole square. Let me check it. Whole square. This is summation xi minus x bar square ka whole square. This is the formula you have when there is heteroscedasticity. So what you do by doing heteroscedasticity robust standard errors, you estimate this from the errors we had I squares and put those values over here. So you actually get values for this and calculate this value for variance of beta.
Okay, sir.
So you actually account for heteroscedasticity. That is what it means. So let's
Bhavesh,
take, yes, sir.
just one last question. So IMC, the beta coefficient in the output what we have got, IMC जो है वो beta coefficient है below intercept.
Right.
Is it the beta coefficient?
In the output, 2 or 1?
The second one.
Sir, this is beta coefficient, INC.
INC is beta coefficient.
Yes,
So,
and we are particularly looking for beta, not alpha.
Okay.
Because beta matters a lot, sir, for us. Definitely alpha also, and in the case of alpha, it is reverse. That I can understand over here.
Right.
But we haven't derived formula for alpha. We are going ahead with beta only.
Okay.
Hello, sir.
Yes.
Sir, can you please show me again the coef test, because I am running the thing, but nothing is coming. Though the comment is showing right.
Just a minute. Coef test. Yeah. Can you see it?
Yes.
So let's take a break. I think there is a
Yes.
need for break for 10 minutes and come back. Then we'll continue with autocorrelation and multicollinearity.